Hi there, welcome back. What we're going to take a look at in this example is given the function f of x equals the natural log of x squared plus 1, we're going to determine analytically where the function is concave up and where the function is concave down. So remember that concavity, that information is found from the second derivative. So we're going to first take the second derivative and then do our analysis that way. So first thing we'll do is take the first derivative. Derivative of the natural log function is 1 over the something, and then times the derivative of the inside, and that gives us 2x over x squared plus 1. And now the second derivative is going to be the derivative of 2x over x squared plus 1, which requires the quotient rule. So what I'm going to do is, knowing that we need the derivative of each piece, I'm going to write the derivative as 2 here, and I'm going to write the derivative as 2x there. And then the second derivative is, well, let's see, it's low d high, which means the denominator times the derivative of the numerator, so x squared plus 1 times 2, minus high d low, so that is 2x as the numerator times 2x as the derivative of the denominator, and then all over low squared. So naturally what we will do is simplify the numerator. So we have, distributing the 2, 2x squared plus 2 minus 4x squared all over x squared plus 1 squared, which is 2 minus 2x squared over x squared plus 1 squared. And that looks simplified enough for now. So what we first have to do is figure out where all the possible points of transition are. And with any expression, that is where it's either equal to 0 or where it's undefined. The good news is, with this one, there is no place where the second derivative is undefined, because x squared plus 1 can never be 0, and which certainly means that the square can never be 0. So that means we don't have to worry about undefined here. So we're just going to set this equal to 0, and there's two ways to look at this. If you have a fraction that's equal to 0, the only way for a fraction to be equal to 0 is if its numerator is 0, or we could just go back to basics and multiply both sides by the denominator, which is x squared plus 1, the quantity squared. Either way, we end up with the equation 2 minus 2x squared equals 0. So we'll solve for x. I'm going to add 2x squared to both sides. I'm going to divide both sides by 2. And I'm going to take the square root of both sides and get plus or minus 1. So those are the possible places where the graph is transitioning between being concave up and concave down. So we are going to make a sign graph of f double prime, very similar to what we did in f prime in the last video to determine increasing and decreasing. Very similar concept here. So I know that I have a possible transition at -1 and another possible transition at 1. And what we're going to do is the same thing. We're going to pick some test numbers. We're going to plug them into the second derivative and try to tell what exactly is happening. Now remember, the first thing is we divided the number line into 3 intervals. So let's just mark those down. This is -infinity to -1. This is -1 to 1. And this is 1 to infinity. So for my test numbers, I'm going to pick -2 for this interval, just because it's close to -1. You could pick anything you want to. On the interval -1 to 1, I'm going to pick 0. And on the interval 1 to infinity, I'm going to pick 2. So we're going to plug all of those into the second derivative to see what's happening. So f double prime at -2 is, and remember, we're going to use the last version of it before we started manipulating it. So we're going to plug it into that. So you have 2 minus 2 times -2 squared, lots of 2's, divided by -2 squared plus 1 squared. Well, the numerator is, let's see, negative 2 squared is 4, 2 times 4 is 8, 2 minus 8 is negative 6. The denominator is 4 plus 1 squared, which is 25, which all that tells me is I have a negative value, which means we are concave down. So I'm just going to draw a picture that looks something like this, just a concave down. Okay, at 0, when we have 2 minus 2 times 0 squared all over 0 squared plus 1 squared. Now, after you work with all the zeros there, the numerator is 2 and the denominator is 1, which is 2, which means we're concave up. So we are definitely transitioning between concavity types there. And then plugging in 2, we have 2 minus 2 times 2 squared, all divided by 2 squared plus 1 squared. And turns out that's the same as if we plugged in negative 2. That's still negative 6 over 25. So that result doesn't change. That means we are concave down. So as far as writing the intervals, it's concave up on the interval. The only interval we have there is negative 1 to 1. And it's concave down on the interval. Well, let's see, we have negative infinity to negative 1. We also have 1 to infinity, and again, those are both intervals that describe the same set of values. So we put a union in between them. Same set of values that are the answer to our problem, I should say. So there are the intervals where the function is concave up and concave down. And just to kind of confirm the results, I do have a graph of the function, y equals natural log x squared plus 1. And as you can see, at those points right there where x is 1 and negative 1, we do indeed have inflection points. Notice it's concave up in the middle, and it switches to concave down as you go to the extremes.